Good evening. My name is Kaunde Audrey. I'm going to take you through the first part of our presentation. Our project is called Reinforced Contrastive Knowledge Distillation for Mental Stress EEG Signal Analysis. So here, our project basically deals with detection of stress in people. And we all know that stress is a problem, it's a major problem, a main disorder in many people, even when they don't realize that they have it. Most people in different sectors, workplaces, schools, healthcare areas, different things cause stress. And so in our model, we're going to be using the EEG signal processing. We're going to be using EEG signal processing to detect this stress and a few other machine learning techniques such as knowledge distillation, contrastive learning, and reinforcement learning, and many that you'll see ahead. So the main problem, our application domain specific problem is that the main problem faced in this project, people are not subjective to these things. One will not just go and diagnose themselves, maybe open your model and say, let me detect my stress levels. It's very hard for people to do that, which makes it a bit unreliable. And the EEG signals require complex analysis, which is difficult to deal with. Much as it's suitable for stress detection, it's also complex. And for the technical computational challenges, we have high dimensionality, whereby the signals capture multiple channels, which makes processing a bit challenging because there's so much that's coming in, and we have noise and artifacts. An example of noise is like if you have an image and there's a shadow in that image. Now the shadow is what we term as noise, because we want the image, but the shadow is going to sort of make the results a bit inaccurate. And we have imbalanced data classes. Here we may have like more non-stress samples than the stress samples, which will make the model biased, and this will make it like less accurate, and it will prevent the efficiency of this model. So the key techniques that we are going to be using, we're going to use knowledge distillation, whereby here knowledge is transferred from the complex models to the simpler models, which improves efficiency, but at the same time maintaining the accuracy. Yeah, it makes it simpler since we're using a simpler model than a complex model. Yeah, then we have reinforcement learning. This continuously refines stress classification by adapting to new data and optimizing decision making. So here it picks the new data, and every time new data comes in, it gets something new from that new data and is able to make decisions on its own later on. We have sparse learning. So for sparse learning, here it selects the most relevant EEG features, reducing computational complexity while maintaining performance. So here it will like take out the different what's not necessary, to leave out anything that's unnecessary. While in contrastive learning, here it's able to differentiate between, maybe now in terms of this project, it will differentiate between stress states and non-stress states, like it's able to clearly differentiate between the two. Then we have the EEG signals, which is able to capture brain activity in real time through sensors and all those different things. Yeah. Then supervised learning. Here we train models using the labeled data, which enables accurate classification of stress and non-stress states. The model is able to clearly differentiate between stress states and non-stress states. Yeah. Then for the last, I'm going to talk about our dataset collection. So in this dataset collection, we have different folders to be used, different datasets where we are able to detect the new responses to different stress situations. For example, when people are calculating complex mathematical problems, or maybe in mental challenge tests, color word tests, horror video, stimulation, and relaxing music. So here we are able to get the signals and detect the responses to those different folders, the responses in those different sectors. Yes. Thank you. I'm going to invite my colleague to take you through the rest of the presentation. Thank you.
Hello everyone, my name is Cindy Emmanuel and I'm here to take you through the other half of our presentation. So here we have some examples of a dataset and dataset images, and from the faces you can tell that some faces seem happy, others seem stressed, others seem sad, others seem like they are crying or they are very depressed. So this talk about the EEG signal processing workflow. So we have the first step is noise filtering, and this removes unwanted signals to improve data quality. Then we also have the methods of noise filtering. We can use low pass, high pass, band pass, and notch filters. So yeah, then we also have wavelet transformation for feature extraction, and this one helps to decompose a signal into different frequency components while preserving the time localization. Then we can use continuous wavelet transform, then also discrete wavelet transform. Then we also have normalization for model training, and this one ensures uniform scale across features, and this helps to prevent dominance of large magnitude features. Then feature selection, where this one sparse learning is applied to extract relevant EEG features, and this one helps to reduce dimensionality and improves efficiency and prevents overfitting. So then the methods we can use, it uses statistical methods like correlation, mutual information. Then they also have wrapper methods and embedded methods. Then model training, and this helps to learn patterns from training data for prediction. And we use here CNNs with transfer learning are used for stress pattern detection. Then we also have classification, and this assigns new data points to predefined categories, and this like reinforcement that like the reinforcement learning optimizes stress state identification. So applications of this EEG based stress detection, we can apply it in healthcare, where identification of mental health conditions and continuous monitoring of stress levels in patients to ensure timely interventions. Like it can be used in psychiatric health centers, and it can help to diagnose some of those diseases. Like now, then we also have workplace safety, whereby if you implement this real-time stress tracking system for high-risk professions, it can help to enhance safety and also provide employee well-being programs to promote overall mental health. Like if you can introduce it in a workplace and everyone can be diagnosed, their stress levels can be determined, so like to promote better working conditions at the places of work. So maybe they can introduce co-curricular activities to improve on that. Then also education, like if the system is introduced in schools, students can be diagnosed like in regard to their stress levels, or maybe approaching papers, or maybe they can introduce like sports or introduce like some sort of entertainment, and it helps them to better understand their learning challenges and develop effective strategies for improved academic performance. So going to the next slide, we're concluding. Talked about the EEG-based stress detection model that was developed using deep reinforcement learning to improve accuracy in identifying stress from signals. And this approach enables the model to learn and adjust over time, enhancing its real-time performance. And the data set serves as a benchmark for future stress detection research, providing a reliable source for training and validating new models. And these are some of the references that will be attached to this video. Thank you for watching. Have a blessed day.